So, welcome to our MLJ workshop. My name is Anthony Bloom. I'm a mathematician here at the University of Auckland, where it's about 2 a.m. in the morning, so early for me. Before I begin my introductory remarks, I'm going to take you over to the resources for the workshop, so you can have a first look at them. So on the screen here, you'll see a repository address. That's github.com/abloom/machinelearninginjulia.com, Julia 2020. So if you just copy that into your browser, if you've not found the link from somewhere else, and go there, I'll give you a few minutes to copy that link into your browser. And we will return to this a second time after I give my remarks. So if you don't get this first time, it's not the end of the world. So I'll now go there myself so that you can see what I'm seeing. So you'll have this repository, and this is where you're going to get the resources, the tutorials that you run interactively as I go through them from this side. So there are a couple of options. First of all, if all else fails, there's just a static version of the tutorials, which is here. You click on that and you get just plain Markdown. And then there's two other options for interactive use of the tutorials. So the first option, which is kind of a plug and play, where you don't have to really install anything, is to launch a Binder notebook. So that's option one. Sometimes that takes a little while, although now I'm reporting that that's sped up quite a bit. The disadvantage with this is it's a little less tested, at least from my point of view. And if you may have to start over if you lose a connection or if you're inactive for about 10 minutes. But in any case, it's a good backup, even if you go for what may be the stabler options, which are to clone the repository and either run an ordinary notebook locally, or to run a script in your favorite IDE. So in the repository, there's this file. It's called tutorials.jl if you want to run a script, and tutorials.ipynb if you want to run a regular notebook. So I'm recommending if you don't have much experience, if you don't have any experience running a notebook, in a Jupyter Julia notebook on your machine, or a Julia script in an IDE, then you could just go for the plug and play option. But I invite everyone to just launch that anyway and see the plug and play Binder as a kind of backup in case your other option doesn't work. So I'm now going to go back to my slides. And we'll come back to this again after I've made the first bit of spiel of the presentation here. So today I'm joined by some collaborators who will be helping us with the questions. They are Thibaut Lienard, Geoffrey Dolphin, Ocon Samuel, and Sebastian Vollmer. The MLJ project is a collaboration between the Alan Turing Institute and now also the University of Auckland. We have a company partner, Equivia, who are actually using this software now. And we've also had help from NESI, which is an institute in New Zealand, the University of Warwick, and Julia Computing. Here's the team. MLJ is designed by myself and Franz Kureli and Sebastian Vollmer. I'm the lead developer, but Thibaut Lienard has also made rather substantial contributions, together with smaller contributions from lots of people. So let me make a little advertisement for help with MLJ, so that you can help an MLJ in ways, both small and big. One easy way to help us is to start the repository if you like it. That helps us. It's one way we can continue to get the project supported. You can help by raising issues. There's no real rules about what kind of issues. They can be problems with the software, or design discussions, or just suggestions, or even help questions. And you can also contribute a tutorial, if you like, at datasciencetutorials.jl. So if you're getting some help and you want to return the favor, maybe you can write a short tutorial on some data that you've analyzed using MLJ. Then if you're a little more ambitious, you might want to implement our interface for some new model that you may have developed. Finally, let me say that we have a 1-year, extending possibly to 2-year postdoc or software engineer position opening up for the project. And if you think you might be interested in that, contact Sebastian at this email address. So I'm the one who gets to do all the talking, and you of course are mostly, you're all muted because there's a number of you. And so how do you interact with me on this in this webinar? Well, you have two choices here. You can there's two text feeds here. You can either use the Q&A, or you can use a chat, which is just like the regular Zoom chat. So what way we'll use these forums is that the Q&A will be for you to ask me questions, but the chat is something that the panelists, we won't be monitoring. So you can use that to chat among other participants. And yeah, so that's the way it'll work. There's also a raise hand option, but I don't think I'm going to probably use that because of the numbers of people that we're expecting here. So who is this software for? Well, basically this workshop, who's this workshop for? This workshop is basically for anyone interested in learning to do some machine learning using Julia software. We assume that you know machine learning principles, so we're going to focus on how you use the software and what it can do. We're not here to teach you about bias versus variance trade-off or any other kind of foundational stuff. You'll be assumed to have some basic Julia skills if you want to actually participate in exercises, but just basic skills. You needn't be a programmer. You needn't have programmed in Julia. And it's helpful if you've already some experience using a tabular in-memory data format, such as data frames or something similar. But in principle, you can follow along without that and even do the exercises. Now, I'm not sure where all that beeping comes from. I'll just have to see. Maybe I can mute that. Okay, so the next question I'm going to answer is, what is MLJ? So MLJ is a toolbox for interacting with lots of different machine learning models. So these could be provided by packages in Julia, but we also interface packages in other languages, in particular the scikit-learn models. A lot of those are interfaced into MLJ. And then once you have your hands on those models, you can train them, you can evaluate their performance, and then you can tune their hyperparameters. MLJ also provides common preprocessing tasks such as data cleaning and type coercion, and it allows you to combine your models. So that's an important part of this toolbox. For example, you probably experience using pipelining from other platforms, and we'll talk more about that later. I'm just going to have a go and see if I can just mute my thing here for a minute, except then that means I'm going to be able to hear anybody, so I might just have to live with those beeping noises. I'm not sure where they're coming from. Okay, so here we go, back to the talk. So why would you want to learn MLJ Toolbox? about MLJ as opposed to using some other machine learning toolbox? There are lots of reasons, I think, but I'm going to focus on two. And the first one is that you're working with one language, at least to the extent that the models that you're using are written in Julia, and a lot of them now are in Julia. So that gives you all the advantages of working in a single language, which most of you will kind of get because you're here at a JuliaCon conference. So that means that you can get under the hood, right? So you can get under the hood and to increase your understanding of the tool that you're using. And it's all written in the same language that you're actually using to interact with the tool. You can get under the hood to customize the behavior. So if it doesn't do exactly what you want to do, then you can change the behavior without having to learn a new language or be an expert in a low-level language such as C or Fortran. Finally, you can even add functionality and contribute to the functionality of that tool that you're using. For example, adding new model interfaces. And that's something that's not too hard to do in MLJ. So if you want to roll your own model, that's something you can do. There are quick and dirty options. And then if you want your model to be something that anyone can use, you can do a little bit more work and do that also. And the other great strength of MLJ, I claim, is that it really has, I would say, a state-of-the-art model composition interface. So rather than model composition being a kind of afterthought in the design, it's something we thought about right at the beginning. And so model composition, that is composing multiple machine models to come up with a kind of a supermodel. This is something that plays well. First of all, it's a very flexible interface. You can do a lot of things with it, and it plays well with everything else that you'd want to do. Okay, so a nice analogy for this that my colleague Sebastian came up with is the Lego analogy. So imagine that you've asked for a machine learning toolbox for Christmas, and Christmas comes around and someone gives you one of the other toolboxes, let's say Scikit-learn or Carrot or MLR or something like that. Well, that's kind of like someone gave you Playmobil when what you really wanted was Lego, right? So maybe you can find a Playmobil set that allows you to play with a train or play with a snake, but what you really wanted was to make a snake-powered train, yeah? And that you can do with Lego. And that's sort of the idea with MLJ. Give you flexibility to really do whatever it is that you want. You're not stuck with the tools as they come. To extend this Lego analogy a little further, you can do things like this. So in MLJ, we have a bunch of different models, and you can inspect those models via this model registry that we'll get into later. And then you may also have some custom code that you want to integrate into your models in some way. So then using this composition, model composition interface, which we call learning network, you can do exactly that kind of thing. And then whatever parameters you may have in your custom code, you can expose them to your supermodel. So that's my introductory spiel. And now what I want to do is just give you an overview of how the workshop itself the rest of the workshop is going to be organized. So I'm going to start with a kind of from the beginning with a brief recap of what supervised and unsupervised learning is kind of about, just for the rest of the of our work here. I'm going to give you a little demo of an advanced bit of MLJ in action by looking at stacking. So that'll come straight after that. And then we'll start the workshop proper. And that's divided into 4 main sections. First, we'll talk about how you should represent your data, and there'll be some exercises. Then we'll talk about, in a sort of central section, about the basic sort of fit and predict workflow, how you select your model, train your models, and evaluate their performance. There'll be a section on transformers and pipelines, and then in part 4, we'll talk about how you optimize your models. The tutorials that we're providing will include a final section on advanced model composition, but I'm not expecting we'll probably have time to do that here. We'll see how we go. Okay, so let's remember what supervised learning is. And here I'm more or less assuming that you know this story, but I think it's helpful to go over it again, if only to assume we're speaking the same language and to introduce some notation. So supervised learning is about learning to predict some variable, which we'll call the target and denote by y, from a knowledge of some other variables, which we'll call x and call the input features, or maybe just inputs. A simple example would be perhaps you're measuring the temperature in the room every hour, or different rooms in your house. So then in that case, your inputs are the time of day, the particular room you're in, and the output, the thing you're trying to predict, based on some historical measurements you've already made, would be the temperature. If we forget the room for the moment, to make things even simpler, then we can visualize the data as just points in a 2D graph. And how are we going to go about making predictions at different times? For example, maybe we want to predict at 2:30 or 2:45 or something, where we haven't measured the temperature. Then what we do is we fit a machine learning model, which in this simple example means fitting a curve. So here's a straight line that attempts to fit the data. Now we can be a little bit more sophisticated and say, well, let's just look at different polynomials, maybe a cubic. That seems to do a little better. And maybe we get carried away now and we try and fit a degree 12 polynomial and get a fit that goes through every single data point, which hopefully you appreciate is maybe not a good idea. So in this model, this polynomial model, we have a knob to turn, right, which is the degree of the polynomial. And this is what we call a hyperparameter. And one of the goals, of course, is to choose what that hyperparameter ought to be to optimize your performance. But how do we measure our performance? Well, we can't measure our performance using the data that the model has seen. That's cheating. So what we need is some new data. So let's suppose now that we actually have measured the temperature on the half hour as well. And we throw away the data that we use to train our models. Now it's fair for us to compare these predictions of our model given by the curves with this data that we held back, right? So we have this holdback set. To quantify that performance, we need to choose a measure or metric, which we could take to be, say, the sum of the deviations of our data from the curve, and take the square root of that. That would be out the root mean squared loss for that particular. So that will give us a number at the end that we can compare for the different curves. And then we choose the curve which minimizes that particular loss function. So that's what supervised learning is, and that's kind of the machine learning workflow in a nutshell. You've got some data, you fit a model, you estimate the performance of that model by how it's going to perform in the real world by looking at how it does on a set of data that you held back from the training. So we also have unsupervised learning, which for the purpose of this workshop, we'll just understand as sort of like supervised learning, but when you don't have a target. And mostly this is going to be what we would think of as data transformations. So for example, a transformation which normalizes the data or which reduces its dimension, for example. So here's a simple example. In a picture of reducing dimension, we've got some two-dimensional data. We fit some new coordinates to our data, which line up with here one direction where the data is varying a lot and the other direction where it's not varying very much. And then we can project all onto this x1 dimension and reduce the dimension of our data by 1. Right. So that's the end of my sort of 5-minute course on what machine learning is about. I now want to give you a short demo of some more advanced use of MLJ, just to help you get an idea of what it can do. And I'm going to look at the example of stacking for that. So this on your screen now is some randomly chosen leaderboards from a data science competitions. And what one notices in these competitions is that teams tend to do well. And the reason that teams do well is that typically people don't just build a single model. Rather, each person in the team specializes in developing a particular model, and then those models are blended together to come up with a sort of super model that's better than any individual model. So one technique for doing that is stacking. Stacking is sort of a fancy version of averaging, if you like. So you take your models, and then you have a judge model. So you have an extra model that decides how to blend those predictions for any new particular observation. So I'm going to go over now and pull up that demo. So this is a demo on stacking, and you don't really need to understand what stacking is. It's just some kind of fancy way of blending the predictions of multiple models. Only thing that I'm hoping to convey is that stacking is not a trivial thing. So it's actually somewhat hard, and it's beyond the capabilities of, say, for example, scikit-learn's model composition interface. So you can't just do stacking with a pipeline. It's more complicated than that. So what in Python you typically do, or any other package, any other platform, is you would use another library. For example, there's a library called vecstack for Python. And if you look at the code for stacking, it's about 8 pages of code, so it's not trivial. The second point I want to make is that stacking, actually, after all, it's not so bad if you use MLJ, right? So here's the code that using MLJ's generic model composition interface, which you can use to do stacking. And instead of 8 pages, you have about 1 page. So this is the code for constructing a stack. In this case, it's just a stack of 2 models. But you can make this generic easily enough without a lot of extra code. So I'll just evaluate that, and hopefully that'll actually work. Yep. So I'm not going to explain that code now, but I'll explain the output here, which is an instance of this new model type, which is representing 2 regressors that have been blended together, regressor 1 and regressor 2, together with a judge model, an adjudicator. And here we have what is the typical case in model composition, where we have nested parameters. So the hyperparameters of a composite model are themselves models. So we have 3 hyperparameters, and each of those is itself a model which has its own hyperparameters. So in this case, the default is just a linear model for everything. So you have, for example, whether I should fit the intercept or not. And let's see this model that we've just instantiated in action. First of all, I'm going to wrap this composite model in yet another layer of composition by sticking it in a pipeline. So that's just the kind of composition where you connect models in a linear, unbranching fashion in a sequence. And in this case, this pipeline is just going to standardize or normalize the input data and the target transformation. That gives us a model now with yet one more layer of nesting. And I can change, if I want to change, say, those default learners, I can do that easily enough just using dot syntax. So I'll change one of the base learners to a decision tree, and I'll change my judge to a k-nearest neighbor regressor. And if I want to, now I'm ready to use some of the meta algorithms available to any model that I like in MLJ. So let's take this pipeline I built, apply it to the Boston data set, and get a cross-validation score. So that's how that works. Here's some different measures, a mean absolute error and the root mean squared error. And then I can, if I want, inspect the learned parameters of our model, and any piece of that particular model. So our models are composite, so I can go inside this composite model and look at the parameters that were learned by the various parts using this dot syntax again. So for maybe I want to know what the learned parameters for the judge look like. So that's some kind of k-nearest tree model, or I could have a look at one of the regressors. In this case, we have a bunch of sets of learned parameters because the regressors get trained on multiple bits of the data in this model. So maybe I pick out one of them. So there's a bunch of coefficients, learned parameters. And finally, you can tune this model using the tuning interface that we'll talk about later in this workshop. Specify a bunch of ranges, and they can be nested parameters. So you can basically tune any parameter in this supermodel that you like using the dot syntax. And I'll just run that. And we'll see that we can access the results of that exercise just the same way we did before. We can go inside and have a look at the results of that tuning exercise, and we can visualize the results. So that's the end of my little demo here of stacking. Now we are ready to turn to the workshop proper. So what we'll do now is we'll go over to, let's have a go back to my slides. This is where you want to go to now. So if you've joined late in this workshop, visit this repository, and this is where you'll find instructions for downloading the notebooks that we're going to be working on during the workshop from henceforth. There should be a link to that on your in the Q&A, I think, at the very beginning. So now I'm going to leave there and go to that actual repository. So here's the repository. And if you read that, you'll find instructions for installing the tutorials. And I'll just go over this once more for those who came late. You've a few options. If you just want to follow along non-interactively, there's the non-interactive, just markdown version of the tutorials. But hopefully you'll have a go at actually running the tutorials. And you have two options. One is to use this sort of plug and play option, which doesn't require an installation at all, which is to launch this Binder notebook. The downside of that is if it drops your connection, you have to restart it, and that might take a few minutes. And the same will happen if you're not active for 10 minutes. You may want to try that just as a backup anyway. The more reliable option, if you've done this before, is to just run a Julia Jupyter notebook locally, or to run a Julia script in your favorite IDE, such as Juno or Emacs. And so the way you do that is you clone this repository, and then you navigate yourself to the file that's called tutorials.jl or tutorials.ipynd. So now I'm going to stop talking for a little while and have a look at some of the questions. And I will start going through the first exercises in the notebook in a few minutes. Let me just load that up now. So here's my version of the notebook, the local version of the notebook. Right. I have a question for the facilitator here. Here's a silly question. How do I answer these questions on the feed here? Where do I click to answer a particular open question?
You should see a type answer button.
Oh, I see. Yeah, sorry.
Answer,
That was a simple question. Right,
or
great.
you can just answer it on voice and click
Yes,
answer
sure.
live. That will take it away.
Yeah, yeah.
But don't worry about that. I mean, you can just answer on the voice and I'll manage to clear them from the screen. That's fine.
I'm just trying to get an idea of the number of questions. So one question that has been asked is, oh, it looks like it's been answered. Too slow. Okay. Okay, I'll send a link to the stacking tutorial. I will not be sending that immediately because I haven't actually uploaded that yet. Okay, so you will experience. Yes,
Anthony. Yeah, you've not answered the question of why MLJ uses @load macro.
Okay, so one of the questions is why do we use this @load macro, or maybe what the question is, what does the @load macro do? So the @load macro it basically looks, as we'll see this a little later. So I'm going to go through this pretty soon. So maybe that's a question that will be answered once I start going through this tutorial. Maybe I'll just leave that for now. But basically, what it does is it looks up the model that you've specified in a model registry, collects the model data, and based on that, it loads all the packages that you're going to need, and then it'll load into scope that particular model type and instantiate it. That's what it does. So one question is there support for feature engineering? So I guess something like feature tools, that is not currently, there isn't a lot of that in MLJ. But there's some flexibility within the model composition interface for doing that yourself, and that hopefully that it's the learning networks which you can the composition interface is something that makes that easier. Yeah, there's quite a lot that gets installed in these things. So I should say that if you haven't, as soon as you get into your notebook, you should do what I'm going to do right now, and which is to run that first cell. Actually, the first cell is up here, which you won't need, which is going to instantiate your environment, project environment, and it's also going to preload a bunch of packages, and it could take a good, amount of time because we've got plots in there and we've also got flux in there, and they kind of seem to take a while. And MLJ is also takes a little while. And then if you're using the binder notebook, then you also want to load this first MLJ cell straight away. So there's a question about time series models. I want to say I'm answering that live. So that's currently a project. There's not a lot of specific tools to time series at the moment. There is an open PR for some time series kind of cross-validation, nested validation, but that's kind of work in progress. Probably won't get a chance to demo clustering, but there is a clustering example in the documentation. So maybe I'll skip over to the documentation now. So here's the manual. You'll find links from the main website to the manual. If you have a look at the section on transformers and unsupervised models, you'll see a little discussion of clustering. I'm not sure that we have any new tutorials yet.
Anthony?
Yes.
Yes,
Jump in.
the 10th lab on the data science tutorials is on PCA and clustering.
Oh, okay, so we do have one, and that is excellent. So we have this tutorial website in addition to the manual, right? And that's called Data Science Tutorials in Julia, and there are links from the notebook. And which one is it? Is it one of the Intro to Stats labs?
Yeah, it's the 10th one. Yeah, lab 10.
So lab 10, right? So that is that's a clustering exercise. So someone asks, is a good question, a fair question. Is there any advantage for MLJ over Python wrapper backend when you're already familiar with those languages? So in some sense, I mean, that's in some sense, yes. Well, if you're wanting to do fancy kinds of a model composition, then of course, if you're familiar with those this lower level languages, you can basically you have a lot of power to do whatever you want. But the question is, how convenient is that? So if you want to, for example, implement stacking, and okay, you're using Python, and you say you're using scikit-learn, you realize you can't do stacking with scikit-learn's pipeline interface, so you want to do that yourself, then for stacking, maybe it's not a great example, because then, well, then you could implement that in Python just fine, because all the slow stuff is in the models itself that you're wrapping. But the idea is that while if you're familiar with another backend, very familiar, that you can certainly do that. What we're hoping to convince you is that with our interface, it'll be easier, and it'll be more that you can do easily. Is there an option to port Python codes into MLJ? You can, if you have a Python model, you can certainly interface it. In fact, that's what we've done with the scikit-learn models. So I'm answering this question live. So a lot of the scikit-learn models can be used from within MLJ. So that's an example of interfacing Python code, I guess. I guess that answers that question. Okay, so now what I'm going to do is, some of you, of course, you're all going to be working at slightly different paces here. I'm going to let others answer the questions for a while I go through the first section of the notebook, give you a little demo of it. And if you're just working independently on your own, of course, that's fine. But I'm going to go through that for the benefit of those who would like that. Once I find the notebook. Why have I? Where is it gone? Might have to do. I don't want to reload it if I don't have to. Okay, I'm going to go find that. Okay, it seems to be here, but is it actually preloaded? Doesn't seem to be. Right. Okay, looks like I'm going to have to reload that first cell as well, which takes a few minutes. So let me just do that. And while that's preloading, I'm going to have a look at some more questions over here. Someone's reporting an error here. Failed to precompile. I'm not sure I know the answer to that one.
That might be hard. The person.
Yeah. So if anyone else has a problem with comma supported value, then give a shout. But it seems to be an isolated case.
Could the person try it again using, because I think he's using Julia Pro. Could he download the installation instead? That should work.
Okay, try using Julia Pro then.
It's already using Julia Pro, so you should use maybe download Julia from the website.
Okay, try using Julia. Okay, so now I'm ready to go with this first workshop. So I'm going to chat for a little while here. So the first thing that I want to explain in Julia, so we're going to start with this section on data representation, how you should represent your data so that Julia is going to interpret it the right way. So one of the things that we use to do that is we introduce this idea of scientific types. So all the scientific type is a Julia type. So these things called scientific types are Julia types, such as ordered factor or continuous or something like that. But they're not types that have any instances. They're used for dispatch.
Anthony, sorry to interrupt.
Yes, sure. Go ahead.
There is a background coming from somebody.
Okay, I'm not hearing it.
That's maybe it's gone now. Maybe I was, but there was some background coming in. But go ahead now. Sorry to interrupt.
Okay, I'll carry on. That's fine. So scientific types are Julia types, which we use to help you focus on the intended use or interpretation of your data rather on the specific way in which your data is being encoded. So and there are basically 4 scalar scientific types that we'll introduce here. One is ordered factor, another is multi-class, so therefore categorical data, and then you have continuous and count. So these things are to be distinguished from ordinary machine types like float or float 64 or string or whatever. So we're making a distinction here between the way you're encoding your data and the way you want your data to be interpreted. So if I look at this first cell, and I probably should have done this ahead of time, but it's all quick. We have this method here called SciType. And what this method does is it allows you to inspect how MLJ is going to interpret any given bit of data. So if I take the SciType of this of 3.141, then out comes this SciType, which is continuous. That's telling you that if you encode something as a float, then all of MLJ's algorithms and models and so on are going to interpret that data as continuous. If I have a bit of a vector where each thing is a float, then I take the SciType, I get an abstract array or abstract vector where the element type is this continuous SciType. Now, occasionally, or not infrequently, you'll have data that's come to you that's encoded one way, but which MLJ is going to interpret the wrong way. So if I look at, for example, heights, and I compute the SciType of a height vector, I can see the element type here is count. So count is another SciType, but it's not what we want here. So I should say count. What is count? Count is for things like the number of phone calls every hour or something, for frequency type data. So potentially unbounded, but discrete and ordered. So in this case, we've got our height encoded as integers, but what we would really want to think of height as continuous, right? So then we need to fix the type. So instead of trying to think, well, what type should I be re-encoding this as, you simply think about how you want it to be interpreted. So in this case, we want it to be interpreted as continuous. And we use this function called coerce then to force our data into the type that we want. So if I run this cell now, I see that MLJ will decide for me what that type should be, in this case, a float 64. So that's what this coerce method does. It allows you to change the encoding of your variable so that it will be interpreted in the way that, by MLJ, in the way that you want. Here's another example of exam mark. Let's have a look at how this vector string gets interpreted. Okay, so in this case, we get a side type, which is a union of missing and textual. But textual doesn't mean categorical. It doesn't. So, and remember, the categorical types were called ordered factor and multiclass. So this is an exam mark. We have low mark, rotten, and we have the best mark, great. So this should be ordered, right? So let's coerce that into that string thing into something that MLJ is going to interpret as an ordered factor. And we'll see here now that that has returned something called a categorical array. So if you know about categorical arrays, that's good. But if you don't, that's not actually too important either. But the point is that this will be interpreted by MLJ models in the way that it's intended, whereas the string won't. Now, in this case, it's a good idea to inspect the levels of this object, because these will come out in the order that MLJ is going to understand them to be ordered in. And in this case, the order is not the one that you want. So you can change the ordering with this levels exclamation mark. These methods actually come from that categorical arrays package. So I specify the thing the vector whose levels I want to change, and then in the second arg slot, I say how the new levels should be ordered. And after I've done that, I'll have the first exam mark is in fact less than the second, which is actually what I want. Now, why don't we just encode everything as integers like you do in some frameworks when you're dealing with categorical variables? Well, the reason is that these categorical data types keep track of all the classes that your variable can take. And so when you subsample, or that is when you restrict to a small bit of your data, the set of all classes is not lost. So if I look at just the first little bit of exam mark and I look at the levels, even though there's only 2 levels seen, all 3 are still there as information that the MLJ models can get to. And this allows MLJ to avoid the common pain point of, training on some categorical data only to find that when you go to test your model on that data, some new class has appeared that you haven't seen before and your model crashes. So I'll just make a comment that there's no special scientific type for binary data. Binary data is either going to be ordered factor 2 or multi-class 2, depending on whether you want to think of your binary data as ordered or not. So that's some basic ideas about getting the types, the encoding of your data right. The next little bit of this first section, I want to talk about two-dimensional data and how you should represent two-dimensional data. So whenever it makes sense, models in MLJ expect two-dimensional data to be tabular. So that's most of the time, actually, for most of the models. And there are exceptions, but that's the general rule. So you don't give your models a matrix, you need to give it a table. Now, Julia has a number of different tabular formats, a large number of tabular formats, and we've designed MLJ in such a way that you can basically use all of them. So there's this nice interface, uniform interface for interacting with tables called tables.jl, and we're using that package so that basically any kind of tables format that's supported by that package, that API, can be used. So I'm going to give just a few little examples of tables that we can think of as that MLJ is happy to use. So the first one I'm going to talk about is a native table. So it's not, you don't need any package to define one, and that's the example of a column table. So recall from above we had these vectors height, exam mark, and time, and we put them into a named tuple, and since they all have the same length, those vectors, that is a valid table according to the tables.jl interface. Now, what about the scientific type of a table now? So far we've looked at vectors, and you can also take the site type of arrays and just scalars. If you take this column, the site type of a table, and it can be any table that meets this, that comes from this collection satisfying the tables interface, then the type is the site type table, together with a type parameter. And the type parameter kind of summarizes what the column site types are. So in this example, we've got two continuous columns. So we've got vector continuous here, and then one of the columns is a vector of missing ordered factor with 3 levels. The type parameter is sort of what gets used for making comparisons between different tables using this operator here. If we want to inspect the actual individual column types, then rather than taking the site type, we use this schema method. So here's a new method, the schema. And if you compute the schema of any table, you get a table that looks like this. So you have the names of the columns, you have their ordinary machine types, element types, and then you have the site types on the right. So we can see we've got this, that the thing named H is continuous and so on. Now I'll give you 4 other examples of tables that you might want to know exist. The other native table is sort of the other one turned inside out, if you like. Rather than looking at a vector of a named tuple of vectors, you look at a vector of named tuples. So that's another way of constructing a table. Like you compute its schema, because it's a valid table, that will work. And another example here would be data frames. So if you really want, these native tables are nice, but if you actually want to do a lot of manipulating with your table, you want to use some more a fancier tabular data format. And the one that most of you, or many of you, will be familiar with is data frames. So I'm going to import data frames, and I'm going to construct a new table data frame out of the column table I already have. So one of the nice things about this, having this common interface, is that that's relatively easy to change between different table formats. You simply take a table in one format and you give it to the constructor of another format, and that just works. So here's a data frame now. Based on the column table that I gave you at the beginning, it will have a schema the same as the one we saw before. And as a final example, or next to final example, you can have out-of-memory tables as well. So here I'm going to designate as a table this CSV file, and I can immediately compute its schema, even though it's just a file at this point. Now, don't get too excited at this point. It's not that MLJ can actually do machine learning with data sets that are out of memory. Not at this point. So generally, when your model comes to actually need the data, it's going to suck all the data into memory to operate on it. And in fact, that's what's happened in this call to schema. But you don't have to explicitly do that. That all just happens when it's needed. So when I call this schema, because it needs to know the number of rows here, it actually will load the file. It'll manifest that file now as an in-memory kind of table. And by default, I think it uses a column table or something. Finally, you may not have your data as a table. It might be a matrix. In that case, you simply wrap it, and we have a wrapper for doing that called you go mlj.table. So then once I've wrapped it, it has a schema. And note that this matrix is not copied, it's just wrapped. And now, thanks to a recent PR, if you were to then unwrap this, so there's an unwrapping version, which is just matrix instead of table, then composing those two things is essentially a no-op. So compiles away, if you like, which is something that happens under the hood, right? These models, these machine learning models under the hood will actually most of the time take your table and turn it into a matrix. So if you do things right, you can avoid that extra costs in terms of wrapping and unwrapping. So the last thing to talk about in this first part of the workshop is how we fix the scientific types in a table every column at once, or at sort of when they're all in a table without unwrapping the whole thing. So to do that, I'm just going to do an example. So this is fixing the interpretation of data in a table here. And we'll take the example of the file that I just mentioned, but we'll turn that into a data frame to make it look nicer. And this is a data set which is part of on the repository there, called the horse data set. And it looks at horse colic, so some kind of horse medical condition. And you see things like fields like whether surgery was performed, the age of the horse, some things like its pulse, respiratory rate, and so on. And so then once you've got this data, you'll want to understand how each of those various variables ought to be interpreted. And that's not something you can leave reliably to the computer, right? So as we'll see in a minute, the computer can make a guess, but ultimately we're responsible for how we think each of these variables should be interpreted. So if you go to the documentation for this data set and you read up about it, or you use your common sense where it's kind of clear, you can figure out how each of these particular variables should be interpreted. For example, the pulse, well, that's obviously a continuous variable, and so on. Now, so our step number one is to see how MLJ is actually going to interpret the data as it's encoded at the moment. So we call schema on this table, and we see we have a bunch of different, a lot of difference between the interpretation and the desired interpretation over here. In particular, there's a lot of count data, which is reflected by the fact that in MLJ, any integer gets represented as a count. And it's common practice for categorical variables to be encoded as integers in a CSV file, for example. So we need to fix that. The first step is to kind of let the MLJ have a guess at what it thinks the types should be. And the way that works is you apply this autotype function to your data. So I've got my table and I apply autotype to it, and it'll return a dictionary of what changes it thinks you ought to make to the data. So here it's changing a bunch of those counts to ordered factors. So this is not the full story, but it's a step in the right direction. So now what we could do is we implement that change by passing this dictionary that we compute with the autotype function to a coerce method. And it's just like the coerce method before, except instead of a vector here, we're plugging in a table. The second difference is that there's an exclamation mark here, which is allowing us to do this in place rather than having to copy everything. That's an option that's available when you use a data frame. At the moment, that's not an option that's generally available because the tables API is very general. It's not just for in-memory mutable kinds of tables. But for the data frame, we've overloaded things so that you can do this in place. So you call that coerce function. That fixes those some of those data types so that they have the right interpretation. So you can see here a bunch of ordered factors coming in. It turns out that all the remaining count data should be continuous. So you can fix that with a second call to coerce, which says everything that's count now, you can make it continue. Please make it continuous. And then the remaining truant entries are fixed. We can fix just manually. And the way you do it is you just pass a bunch of pairs here, the name of the column, and then the scientific type that you want. So we can specify multiple ones at once. And then when we've done that, we've now fixed the types in our data so that they're all going to have the right interpretation. And that's the end of part 1 of the workshop. So there are a few resources here specific to that, what I've just talked about, given here. And if you want to try them, there are some exercises to help you kind of determine, to practice, and what we just talked about. So now I'm going to stop talking for a little while, maybe about 20 minutes, and try and help out with questions while you absorb this material I've just discussed, if you haven't already, and have a go at the exercises. There was a question about the demo, the stacking demo. I'm going to push that to the repository, which I hadn't done. It could be that it's just a script. I'm not seeing the... Oh, there it is. I guess the script was already there, but the notebook wasn't. So I'm going to. Oh no, they're both there. Now. Okay, no, they weren't there. So the notebook, which is demoing the stacking, is called WOW, W-O-W, and that should now be on the repository. Let's reload that. So it's available as either as just a script or as a notebook, if you want to have a look at that. So there's a question here, is there a difference between types continuous and abstract float? So, well, yes, they're different for a start. So continuous, I guess the question is really, maybe the question is, how would I know exactly without actually trying out the psi type? Maybe this is the question that's really being asked. How do I tell how ahead of time how something's going to be interpreted? Or let me answer this question. Something will have a psi type of continuous if and only if it is an abstract float. So that's true. So in that sense, there's no difference. If you want to know exactly how, what is the convention that MLJ is using without going and trying things out manually with psi type, then what you want to do is visit this this particular repository, which is called MLJ Scientific Types. And if you go to the documentation, you'll find, first of all, you'll find more about this scientific type business. There is another package, by the way, which is called just Scientific Types. This is which is a very small package which defines the types, but it doesn't define a convention. It just says, okay, we have things called continuous count. Here are some types without any instances, a little bit of hierarchy, but it doesn't tell you, it doesn't make a decision about how you want to, what machine types will be interpreted in what way. So for that, we look at MLJ Scientific Types, which is where MLJ actually specifies its convention. If you go to the documents there, you'll see on the first page there a summary of the convention. So for example, anything that is a categorical value, this is our case, for example, which is a type from the categorical arrays package, then that will be either an ordered factor or a multi-class, depending on the value of a particular attribute, which is the ordered attribute there. So it's all kind of spelled out here if you want to go a little deeper into what that convention, MLJ convention is. So there's a question, do we need to add the scientific types to support psi types? No, it's just something that's re-exported from MLJ. So if you go using MLJ, then all the scientific types are available to you. So if I haven't answered the question about the difference between continuous and abstract floats to your satisfaction, Alexander, go ahead and answer and ask a new question. I'm just going to close the question. So this looks more like a suggestion here about the question is how do scientific types compare to contrasts? For example, contrast coding, dummy coding. I'm not sure I understand what that is. Maybe someone else knows about contrasts and can answer that. And the rest of the question is for the continuous types, you have bounded, censored, truncated variables, non-negative, and so on. It would be nice to see count data generalized to rates per time to event and so on. So that sounds like more of a suggestion, but so I mean a rate. So if a rate, I guess we would. So there's always a little bit of a grey area, and I mean a rate could be something you might want to think of as continuous. It kind of depends a little bit on the model and what you understand, how you understand a model to interpret the data. Sometimes whether you want to interpret think of something as, say, a count or as a continuous or whatever. But it sounds like a nice suggestion worth thinking about, but I haven't thought about this contrast data before. So someone's asking why, if I have a vector and I take its psi type and then I look at a smaller version of a vector, why it returns the same psi type. Well, it wouldn't be very different if you would just take the type of that vector, right? So a psi type is sort of like, if that helps, maybe I'll just do a little demo here to answer that question. It looks like someone's already answered it, or it's been dismissed, but I'll go ahead and talk about it anyway. Let's go over to here. If I have a vector, say, I don't know, some random vector, and if I take its type, right, its type of, and then, or if I take the type of some portion of that vector, then they have this the same. Sorry, you think I've been doing Python, but I haven't. They have the same type. Whether the type of a vector is, whether you take a bit of it or not, is going to be this. It's going to have the same type. So psi types are sort of the same thing, right? A psi type is something like a type, except it's telling you how something's going to be interpreted rather than it's telling you what its specific encoding is. All right, what other questions do we have here? Oh, someone's asked, is there something like union interpolated continuous / continuous as a means for tracking data that was imputed? No, we haven't anything like that, but it sounds like a good idea. So raise an issue. Good question. I don't see any reason. That might be a good thing to introduce into the psi type framework. Thank you, Christopher. So in case you didn't notice, there are answers to exercises at the very end of the notebook. So I haven't put links along the way. I didn't want to make it too easy. But if you go to the top, you can click on solutions to exercises and it takes you to them. I don't know if I've done you a favor by telling you where the solutions are or not, but they exist. Here's another good suggestion, which we haven't implemented. Is there support in the psi type framework for context variables? For example, something for example, non-informative variables, I guess, like an identifier or something. I think that's the question. And if I think the answer is no, but that's a good idea, feel free to raise an issue on the repository. So Kevin Squire, I'm not sure if that's a question. Is it a suggestion for me? You want me to change my environment variable? Maybe you could say specifically what, is there something you're not seeing clearly about a notebook, or is it about something else that I'm displaying? I'm not sure how to address that question without more information. Oh, okay, so that was a general suggestion for anyone. So if you have a general suggestion, maybe the best thing is to put that in the chat rather than the question box. Thanks. Okay, I think I'm going to move on to the next little bit of the notebook in a couple minutes. So some aspects of the side type may become clearer once we see them in action in modeling. So, I mean, the point perhaps that I didn't make, which I should have, is that MLJ models are going to articulate their data requirements in using side types. So, for example, a model is not going to say a decision tree or whatever. It's not going to say, you need to give me float 64 data. It's going to say, I need the data to be continuous. So you focus on how the data, you want the data to be interpreted, not on a specific type, but also the models are forced to articulate their requirements in the same language, so that you don't, otherwise it would be kind of silly, right? So, and we'll see that in the next section that I'm going to start. If not in the next part, then in the one after. I think it's in the next part. Okay, so I'm going to now have a look at the next part of our workshop. Somehow I'm racing around. So the easiest thing if you get lost here is just to go to the top of your notebook and then go to the contents, right? So I'm going to go to part 2, selecting, training, and evaluating models. So in this part, this is kind of a longer section than the others, and it's kind of, in some sense, a core part of the workshop where we get into the fit and predict workflow. And our goals are going to be the following. I want to show you how you search MLJ's database of models to identify a model that's going to meet your particular needs in terms of the task you have at hand. And then we're going to see how we evaluate the performance of a model once we've picked one, using, in the first case, with doing it with our bare hands on a holdout set and using the fit and predict workflow. And then, well, along the way, we'll see how it is that you can inspect the outcomes of your training and save these results to a file. And then we'll introduce some boilerplate code which allows you to do the kinds of things we've just done more efficiently, and to do fancier kinds of performance estimation, so using cross-validation. And finally, we'll see how you can examine how performance varies with a fixed parameter by looking at learning curves. So the hello world of machine learning is to classify Fisher's famous iris dataset, right? So let's have a look at the iris dataset and use that as an example. For variety, I'm going to grab this dataset from OpenML. So let's have a look at OpenML. You may not have heard about OpenML, so I'm going to give it a little plug. OpenML, the easiest way to describe it is that it's something like Kaggle, but open source and sort of for academia or whatever. So they have different things. They have data sets, and then they have interfaces to various machine learning platforms like scikit-learn and R and so on, which allow you to kind of upload and download tasks and flows and runs and things. I'm not going to go into detail. The only thing we're going to be using here are the data sets. So if I click on data sets, and this is the only thing so far that MLJ is interfaced with. But look at the data sets in OpenML. Oh, it's taking a long time to load. I'm not sure why that is. Okay, so while that's loading, I'll go back to the tutorial. And hopefully this won't take too long to load. So here I'm gonna actually pull a data set down from OpenML, the iris data set, which happens to have the ID of 61. And I'll explain this ID business in a minute once it's loaded there. So there's this command openml.load to load the data set. And then again, we're just going to turn that into a data frame. We don't really have to for this exercise, but it's probably the form that most people are used to using, and it will allow us to view things in a convenient way. Now, this is charming. It looks like OpenML is having some issues here. Okay. Can anyone else ping in the questions here if you're having a problem with OpenML, or if it's just me? Someone want to just, or perhaps one of my helpers want to try it, say if they're having problems? Okay, so that's fine. We have a plan B. So we had some problems with OpenML earlier in the week. I'm going to abandon this. Now this is going to muck up the notebook a little bit. What we're going to do is we have a built-in canned version of the iris dataset. And the way you load it is by going @load iris. So we're going to do that instead. Now we're going to pay a little bit of a cost for that because it turns out that the feature labels are a little different. So we'll just have to fix that as we go. Now this is taking a while, but probably for some different reason, maybe because data frames hasn't been loaded yet. Someone managed to load the data set from OpenML. Now I'm wondering why all of a sudden this is taking a while for me. So if you like, you can stick with OpenML. Maybe the problem is that my notebook has died for some reason. Now, I'm not sure what that is, but what I'm going to do is split this into two here. Let's just load the data set first. So there's the data set. Now, why doesn't it want to make a data frame out of it? Oh, I see. I know what I've done. So we shouldn't use the macro version. We should use this version here. So the macro version splits it into an X and a Y. This one doesn't. So you can either go with the OpenML data set if that's working for you. Maybe I'll just try one last time here. No, I've already gotten rid of it. Finally, I got it. Okay, maybe I'll go back then and try and do this with OpenML. It just seems to be slow, but it's not. It is working. So how do I do that? Right, I go OpenML, and it's 61. Now I'm getting it too, and we'll put that into a data frame. Okay, success. So it seems that that's just taking a little while. So the data set consists of a bunch of continuous features and one feature that is the species of the plant, and which is normally the thing you want to predict. So our main goal in this next little while is going to be to predict the class variable. It's called class. That's the name of the variable, which is the species, given the first four continuous variables, the measurement variables. Our first step is to inspect the scientific types of our data. So we do that with the schema, and we see that things are actually in good shape. So the things that should be continuous are, I mean, these are lengths and widths that they ought to be continuous, but that the last variable, the class or species, is textual, but we want that to be multi-class, okay? So we're going to coerce that with the coerce exclamation mark method. And now our schema is correct. The next step, once we've got our types fixed, is to horizontally split the data. So that is, we want to separate out the bit that's inputs from the bit that is the target that we want to predict. And for this purpose, MLJ has a command called unpack. There's quite a bit you can do with unpack, and maybe you want to have a look at the doc string for details. Let me just explain the basic functionality. So what you have is the first thing you plug into unpack is just the table that you want to split up horizontally here. And after that come a bunch of filters, or predicates, what do you want to call them? One for each thing on the left-hand side. So I've got Y and I've got X here. So what this first filter here is saying, so this is just a function which is either true, going to evaluate to true or false, depending on the name of the column that I'm going to give it. So this first filter says, am I equal to the name, column name, class? So if that's true, then that column is going to get unpacked into this first variable Y. And since it's just a single column in this case, by default, that will be a vector. Then we come to the next filter, which is just a trivial filter or predicate that says, I'm always true. So that means that everything that is left, everything remaining after this previous filter has been examined, gets unpacked into the second variable X. So, and then we specify a seed or a random number generator if we want the rows to be shuffled at the same time, which we are going to do. So basically, at the end of the day, Y is going to be the class and X is going to be everything else. And I'm going to call that, and then I'm going to compute the psi type of just the target, just to make sure that that came out correctly. And it's a vector, and it's multi-class. So in case some of you are quite new to Julia, the most important command to know is how to get documentation on a string, right? And the way you do that is you go question mark, and at the REPL or in a notebook, you go question mark and the function you want to learn about. And there's doc strings for most of MLJ's functions. So now that was kind of step 2, splitting the data horizontally. Now we're going to go, so I'm giving you a sequence of steps. I think there's 4, which is sort of part of this main fit and predict workflow. But now I'm going to go on the side here and tell you how we identify a model to use. So first of all, if you want to see all the models that are available to MLJ, you just call this function called models with no arguments. And you get everything plus the kitchen sink. Too much to be immediately helpful, in fact. So here is the currently 142 models. Well, actually not all of them because they don't fit on the screen, that MLJ can put at your disposal. Now, what you're actually seeing here is metadata for the models. So each entry in this big long vector is a name tuple with metadata about a model that you can load. The models are not loaded, most of them are not loaded a priori. You have to load the package that you want when you want to use the particular model. So let's have a look at one of those entries, let's say the third one, in some detail by just picking it off. And then we see all the different things that we can know and learn about this model without actually loading it. Including in this load path here is instructions on sort of for MLJ on how to find that model. So there's things like the name of the model, the package that provides it, whether it's supervised or not, and then coming down some stuff about hyperparameters. And then coming down, I want you to focus on these last few things here. So there's this thing called the input side type, and there's this thing called the target side type. The output side type is something that's more relevant when you're a transformer, which we'll talk about later. So these traits here, this metadata is telling us, what kind of data this model can handle. I think, what is the model? It's add a boost ensemble regress or whatever that. So it's basically saying that if we unpack this, that the input side type, the inputs that you're allowed to use with this model must be tabular. And then there's that type parameter business I mentioned before, which is if you unpack it saying, well, each column has to be continuous. And the target, in this case, the target variable y, it's saying it can be any vector that's continuous. So in other words, this is a regressor. So if this were a classifier, then this would be some kind of finite side type like ordered factor or maybe just finite, which is the abstract type sitting above ordered factor and multiclass. So let's pick off one of those things to look at a bit more detail, and we'll call it we'll look at the target side type. And here's how you test whether the particular target you have in mind is going to work. I mean, ordinarily we don't do this way, but I just want to kind of give you some understanding of how all this is working under the hood to help you build a model of how MLJ is working. So let's do that here. Let's compute the side type of our actual target and see, is that a subtype of the target side type that is declared by the model metadata? And in this case, it's false because our target is categorical, but the model is looking for continuous. So this model won't do. So now, how do we search models in a more fine-tuned way? Well, for that, we define filters based on these various traits here. So these are actually traits, if you know what traits are for the models. But you can also just think of them as keys for this named tuple. So we define a filter, and here's an example of one where we look at the metadata and we peel off its target side type and we ask, well, is abstract vector finite? This is the side type relevant to classifiers, a subtype of its particular target side type. And let's make another restriction that it should be a pure Julia model. Now, again, the casual user isn't probably going to necessarily do this, but I want to just give you an idea of how things are working under the hood. So once you have your filter, you give that as now an argument to models. And it'll restrict now your model list to the ones that have the right target side type and that are also pure Julia. The other kind of search you can do is you can search by string, where the string is something living in the name or the short doc string that is attached to each model. So you could, for example, just look for everything that looks like maybe it's a classifier. And then finally, there's the tool that you'll probably use the most, which is to construct automatically your filter from your data. So suppose you have, as we have here, some input data X and some target data Y. Then you give that data in this order to the matching function. So here's a new method called matching, and that generates automatically for you the filter which you want to give models to find all models that will work with that data. So, and there they are. There's 42 models that will work for the iris data set. Okay, so that's a little aside about looking for models. Now let's choose a model and load the code we need to put its type into scope. And the way we do that is with this @load command. And if you're curious actually what is going on, you can add a verbosity argument here, because there was a question about it. I'll do that. And let's see what that does when I call that command. It's telling us it's importing the package called MLJ Flux, because the model I've picked is a neural networks classifier, and that's the package it belongs to. And so that's what it's doing. And then it's also importing this particular type name into scope. The second thing that it's doing is that it's going to instantiate an instance of that type with the default hyperparameters. So that's what model will be. So this thing that you see shown here at the very end that got displayed is how a model instance looks, which is like this with all the hyperparameters listed and their values on the right. And in fact, they're yeah. So this is a neural network from the Flux package, or a wrap of that, and you can see things like regularization parameter, batch size, number of epochs. And here this builder, I mean, we're not going to talk about this in detail, but I just mentioned in passing, this builder here is sort of like instructions for how to build the neural network once you see the data and know, you know, how many columns you have and what, and so on. So that's how you load a model once you've picked one. In this simple example, so we'll see later that sometimes there are the same model name is provided by multiple packages, and then you have to specify the package as an extra argument. We'll see examples of that later. So now once this model code is actually loaded and we have an instance in scope, if we wanted to, we could actually get all that metadata again using the info command directly onto that model instance or the model type. It doesn't make a difference. Now I should make an important explanation about what we mean in MLJ when we use the word model. So this is maybe different from other framework that you've worked with, but in MLJ, a model, or when we use the word model, we're just talking about a container for hyperparameters. So what you see here is what you get. There's nothing more in this struct model apart from than what you'd see here, which are the hyperparameters. So the things that the model is going to learn, the learn parameters, so for example, the weights in this network, or the coefficients in a linear model, those learned parameters are not part of this model object. The model object just specifies the hyperparameters. The learned parameters are going to live somewhere else in this thing called a machine, which I'm going to introduce in a little bit. And now we can change, these are mutable, these models, so if you want to change one of the hyperparameters, you just use dot syntax as normal. And every model comes with a keyword constructor so that you can instantiate them that way. And so that's, you know, doing this is the same as what we've already done above. Okay, so now we're going to talk about fitting and predicting and how we inspect the results of training. Someone's asked, I just noticed because I looked up, how could I use matching XY and only get Julia models? Probably that is an accident, or maybe you're not, that's a bit surprising. Maybe I'll let someone else address that in detail, so I want to continue the discussion here. So, right, so now we've got a model, and the next step in the fit predict workflow is that you bind your model to data in what's called a machine. So you think of a machine as just data plus a model. And ordinarily, you give this machine all the data that you've got available for training, for validation, and maybe for testing. That's a choice for you. You don't have to give it all the data, but that's often convenient. So we'll do that. We'll take this model, which is just a set of hyperparameters, essentially, and the data in this order, and construct this thing called a machine. And it's the machine where the actual learned parameters are going to be stored once we train it, once we fit it. The machine also stores some other information which allows training to be, in some sense, clever, as we'll see in a minute. So our next goal is going to be to train this machine, and we're going to train it on 70% of the data and evaluate it on a 30% holdout set. And to do that, we're first going to make a split, but rather than splitting the data itself physically, we're going to split a view of the data. Or in other words, what we're going to do is we're going to take the row indices, and each index Y is just sort of fancy for all the row indices from 1 to the length of Y. So we're going to take that row of all row indices and split it into a train set of row indices and a test set of row indices. And this number here, 0.7, means train should be 70% and test should be the rest. And you could put three or more things on the left here, so long as you put more numbers on the right. But we're just going to stick to a train and a test set. And so now you see here, we've got from 1 to 105 is our train, and then the test is all the rest, which goes up to 150, which is the total number of rows in this data set. So now we fit the machine and we specify which rows we want to train it on. And in this case, I'm going to turn the verbosity on so that you can see some detail. And normally you're probably not going to bother. Oh, this is taking a little while because probably we're loading Flux now, which is one of those packages that takes a little while. Okay, so there we go. Now I've made this a noisy operation here because I want to have you have a sense of what's happening in terms of iteration. So this model happens to be an iterative model. It's a neural network, so it's learning by gradient descent, and it iterates over epochs, right? And in this case, we have an info output here telling us what the loss function was, the training loss for each epoch, and there's exactly 12 of those because we set the number of epochs to be 12. Okay, so I'll come back to that observation in a moment. Next, I need to just tell you how we predict. So predict is just the obvious thing, give the machine, apply predict to the machine. And now we have a choice. We can either specify the row indices, or we could give it new data, because, of course, eventually we want to give our models data we haven't seen at all before. So, but for convenience, I'm just going to look at the test rows and predict on those. And, oh, I don't know why I didn't restrict this. Let's make this, let's have a look at just the first few rows of this. So we're seeing here predictions, and this model is actually a model that predicts probabilities. So it's what we call a probabilistic model. And so the predictions in this case are probability distributions. Now I'm going to come back to that in a minute. So we'll talk about that in a little bit more detail. So you don't just see raw probabilities here. It's something a bit more complicated. Okay, before the next thing in my notebook here is explaining how we inspect the learned parameters of our machine. So there's a method for that, and it's called fitted params. Incidentally, while I think of it, I've put a list at the very top of this notebook under resources of all the methods that we introduce in this workbook. So if you just can't remember what the method's called, you can look at that list. So here we see that a a flux chain is returned, which is basically the neural network that, with all its weights, they're not explicitly appearing here, but they're buried. You can access the weights by accessing this object. So that's what happens when you go fitted params. You get a named tuple where the names tell you what the thing is, and yeah, that's how you inspect the learned parameters. And then every other kind of thing, every other kind of outcome of training that you might be interested in and that the implementer has chosen to expose to you will be available in the report. So we separate the learned parameters from everything else, and everything else gets put in the report. So for example, here we have all of the training losses are in the report, but we don't think of them as learned parameters. If you want to save a machine that you've trained, there's sort of obvious syntax for doing that. I haven't tested this a whole lot, but I haven't had a lot of, we know that some models, this format doesn't work, but for some, as far as I know, this works fine. And then if you want to retrieve a model that you've saved before, you just use that machine constructor again, but instead of giving it a model and some data, you give it the string for the file name. And then you can, of course, predict on that machine just as normal. Now, because you don't save the data, you can't now fit that machine again. But if you wanted to fit using the hyperparameters that went along with that model, you could then add that data to your constructor. So there we go, we went and fitted it again. So now the next thing is to talk a little bit about the sense in which training of models can sometimes be clever. And using this example of the iterative model, because iterative models are things you want to train sort of more sensibly. So if I increase the number of epochs in my neural network regressor, I don't necessarily want to restart the whole training process from scratch. I want a warm restart, right? That just adds 4 more epochs. And that's what will happen by default for this model, because that's the way the model is implemented. So the machines are keeping track of the last hyperparameters that you used so that it knows automatically to do this. So if we just do that, add 4 more parameters, and we see that although the number of epochs now is going to be 16, 12 plus 4, only 4 more iterations have happened here. So we've had a warm restart. For this particular model, there's another parameter which will not trigger a restart when it's mutated, which is the learning rate. That behavior can be altered by a certain hyperparameter. But ordinarily by default, when you change the learning rate, that doesn't restart training either. So then you can accelerate the model after some iterations, if you like, by increasing the learning rate, as we've done in this example. However, if you change any other parameter, which really does, indicate you need to retrain, for example, the regularization parameter here, then, training is going to restart from scratch. And that's the typical case. But whenever you have an iterative model, hopefully the model has been implemented in a way that the retraining is smart in the sense I've described. So now I'm just going to silently retrain this model from scratch with 50 operations. Oh, not from scratch, actually, but I'm going to make sure the total number of epochs is 50. And I'm going to make a prediction. And I'm going to look at the very first prediction and explain, as promised, this business about the probabilistic predictions. So in other frameworks, you're probably used to seeing a vector of probabilities here. But in MLJ, we made the decision that when you have a model that can predict probabilities rather than making point predictions, then it will do so by default. So this is not predict prob or something like that. The predict method by default will predict probabilities if that's the kind of model, the kind of thing that model can do. And the second thing is, rather than predicting some probabilities in some mysterious order here, the raw probabilities or parameters or whatever, we always predict, as far as when it's possible, a distribution object. So there's a package called distributions, which some of you will be familiar with, which which provides a type-called distribution. And for all the models so far that we've implemented in MLJ, the predictions are of some subtype of this distribution type. Now, in this particular example, we have an ordinary finite target, and for finite targets, so that's a probability distribution is just a vector of probabilities, and they're wrapped in this distribution which is called univariate finite, and this is actually not part of the distribution package because for various reasons we've defined a new type because the data comes with labels and because we want to track all the classes, as I talked about earlier. So what we see displayed here is the probabilities for each particular class. So there's a probability, say, of 81% of getting a versicolor in this particular prediction. So we can tell if we have a probabilistic model by looking at that metadata I told you about before. It includes something called the prediction type. And I think I've summarized mostly what's in that important section here. So now what if you want to get at these probabilities? The way you do it is you use the methods that are provided to you by this distributions package. So this is going to be generic for any kind of probabilistic model. You'll always be using the same kind of methods to access the information. So, for example, there's this PDF method, which allows you to access the probability density function or the probability mass function in this case. So if I want to know the probability of iris of the Virginica thing, I just call PDF like that, and it gives me that probability. If I want the most likely observation, then I apply the mode to that probability distribution. So the most likely one in this case is the versicolor. And if you've got multiple predictions, then you just broadcast these methods using just ordinary Julia methods here. This is nothing MLJ specific. Now, it may be that you're actually not interested in these probabilistic predictions. You just wanted a deterministic prediction at the very beginning. You don't care about the probabilistic prediction. And in that case, you can just, instead of using predict, you can use predict mode. And that will just straight away give you the predictions, and you don't even have to think about the most likely predictions rather than the probabilistic ones. Now, if you want to see the probabilities in a more kind of conventional way, you can also do that. We've overloaded this PDF function in a way that allows you to do that. You specify your predictions, a vector of probabilistic predictions. You plug in the levels, which will come in a certain order, and then that will determine how the columns are ordered in this matrix. However, doing this is not as useful as you think you imagine it might be if you've used another framework, because MLJ is really set up to work with these probability distributions. So, for example, if you want to apply a metric, such as cross entropy, then if it's a probabilistic metric, like cross entropy is, it will always expect as your prediction variable in the first slot, it's expecting a vector of distributions. It's not expecting this matrix. Okay, and then the right-hand side, you put in your predictions as usuals. So I'm going to now compute the cross entropy and take the mean, because that actually reports something for every single observation. And I get now finally an estimate of the performance of my model on the holdout set. Now, if we wanted to apply a deterministic metric, like the misclassification rate, then we need to apply the mode first to our data. Oh, unless we use that predict mode method, of course. So here's the misclassification rate. Now, while we're on the topic of metrics or loss functions or whatever you want to call them, all those kinds of things are collectively called measures, which is kind of a broad term for things like that in MLJ. Then you can use the measures function like you called models before. You can also do the same for measures and get a list of all the measures that are available. And you can do kind of a matching search. This is somewhat experimental, but if you have a particular target variable, you might want to look at just the measures that potentially apply to that target variable. Right, so we're getting close to the end of this longer section. maybe another 5 minutes. So now the next thing is to tell you how to do all that stuff that we just talked about without actually doing it with your bare hands. So suppose I have a model. I've bounded in the machine to some data, and I want to evaluate its performance on a holdout set. So all you do is you just give this machine to this evaluate exclamation mark method. It's mutating because the machine is going to be trained, so its fit result, the learned parameters are going to be changed throughout this exercise. So then you specify the kind of resampling you want to do to make that estimate of performance. So in this case, we're going to use a holdout because that's what we did before, and we want 70% of the data. So that's what we mean by resampling. Here. And you can specify a battery of metrics you'd like to apply. And then you get a named tuple, which organizes the results. So this is a property accessible object, but it just happens to be displayed in a table. You have information per fold, but since this is holdout, there is only one fold. So let's have a look at another option, which is to use cross-validation. And we'll use 6-fold cross-validation. So all we're changing here is the resampling strategy. And I'll make the screen a little smaller so we can see all that better. Is we see for each measure, we have an aggregate measure, and then we have measures for each in particular cross-validation run, like each particular fold or sample, however you want to call it. There's even per observation estimates of the loss or whatever it is, if that loss function supports it. Another possibility is to do Monte Carlo cross-validation, where you repeat the cross-validation many times and randomize the choice of folds, so which you implement by giving cross-validation a random number generating seed or an actual random number generator. So that's another alternative. That's a little bit too much to look at. And I think there's also stratified resampling if you want to try that out. So as I've mentioned, there's different things you can access from what Evaluate generates. There's the measure, list of the measures, the corresponding aggregate measurements, and the fold, and so on. Now, I make the final comment that in this Evaluate, you could restrict the rows that you use. So perhaps you want to save out a final test set or something. So I've split the data again here and reserve that for a very final look at the data estimate of the performance, and do your cross-validation on everything else, the train set. So then you just specify rows when you call this Evaluate function, and it'll do that for you. Okay, so in this final subtopic of part 2, which is kind of the longest part, and we're almost done with it, is learning curves. So it may be that what you want to do is look at the performance, but you may want to look at how the performance evolves as you change one of the hyperparameters. So in this case, what we're going to look, the hyperparameter we're going to pick is the iteration parameter, so we can see just how long we may actually want to run our iterations. And we want to look at out-of-sample performance, right? We don't want to look at the training loss. We want to look at an out-of-sample loss. So we do that by specifying we're going to use a holdout strategy. And the reason that we're going to use the holdout strategy is that'll be a lot faster, and because the smart retraining business will mean that each time we increase the iteration parameter, it's not going to, have to restart, because if it were cross-validation, it would have to restart every time, of course. But by using the default, which is holdout, that won't happen. So anyway, let me go into this in a little more detail. The first thing we need to do if we want to plot this learning curve is specify a range. And the range construct, what you do is you give the range constructor the model where this hyperparameter comes from. you specify the name of the hyperparameter, so in this case epochs, and then you give bounds on the hyperparameter and a scale from which to select the points within that range. So we're going to use a log scale here. We'll talk a little bit more about ranges when we get into tuning later, but I'll just that's all I'm going to say about it for now. So then to give you a curve, and what this learning curve function actually generates is not a literal plot, but the information you need to generate a curve, but we'll call that curve anyway. You give it a machine, which is, remember, just a model plus data. You specify the range, the resampling strategy that we want to use to estimate the performance, and the metric that you're using to measure performance. And then you can go ahead and plot the curve by extracting from this curve the relevant bits, in this case parameter values and measurements, and add some decoration to the plot. So I'm going to call all that, and that might take a little bit because I'm not sure if plots has come loaded into this yet. First it's doing the generating the data. So essentially this learning curve is kind of like one-dimensional tuning. It's actually implemented as one-dimensional tuning, a one-dimensional grid search. And we'll talk about tuning in more detail in part 4. No, I think it's just loading plots now. Okay, so there it is. So there's a learning curve. It shows you how the sample estimate of performance is falling down as we train the network. And that's the end of part 1. I'm going to finally stop talking for a little while and let you play around with that part of the notebook and have a go at the exercises if you're so inclined. And so I'll start the third part of the workshop in about 20 minutes. Is it going to work? Let's see, we've got about an hour and a half left. Yeah, I think that should be fine. In terms of questions, you oh, well, okay, don't mind. So there's a question. Am I correct in assuming that MLJ has none to minimal performance hit, since it's just an interface to, for example, Flux? The answer is yes. It depends what you mean by performance. So in terms of if you're having a very large data set, there could be some issues with copying of the data. I mean, but the data is not going to get. There could be some, just as so. I mean, yeah, that could be the only issue. But in some sense, that may not be a cost, depending on the particular table format that you use. So, for example, if you're doing something like you're using, say, you may be doing. Maybe hopefully what I'm about to say is correct, and I may need to check this. If you're using the image classifier from MLJ Flux, then or maybe let's pick a different example. Suppose that you're doing ordinary regression, have a regression problem, and your data is already in the form of a matrix rather than a table, just for example. Then if you would wrap that matrix as a table and give that to MLJ, then Flux is going to turn that into, or the Flux interface is going to turn that into a matrix, and there's not going to be any copying going on in that case. So sometimes by choosing the right format for your table, you could avoid that copying. This is something that we're still looking into to avoid this kind of cost. But apart from that, there shouldn't be any kind of performance. I mean, in terms of, you know, resampling and tuning and those kinds of things, most of the work, of course, is happening in training the models, which is happening within those models, and it's not a cost that you're paying, a big cost that you're paying. So, and by extension, would I ever want to use base flux rather than using just MLJ? And that's a really good question. That kind of depends on your use case. So the idea that there is always, so in terms of doing deep learning, you know, there's always going to be things that you could do using flux that you won't be able to do through an interface like MLJ. And that's by the nature of MLJ. MLJ is trying to be a universal interface for models that come from, you know, a whole spectrum of paradigms. So not just deep learning models, but probabilistic programming models, conventional models, and so on. So if you want to build an adversarial learning network of some kind, I don't see one using MLJ Flux to do that. The idea by interfacing Flux, though, is that for sort of the casual user, there'll be an awful lot that they would want to use something like Flux to do, and they won't need to. It'll be more convenient to use MLJ if one wants to do things like cross-validation, or one wants to do, eventually, we haven't got this implemented yet, but if you want to do something like cyclic learning rates, then there'll be boilerplate code that allows you to do that for any iterative model, and you'll be able to do that for your Flux model using MLJ more easily than you would with just Flux, because Flux may not provide all that sort of meta functionality. So it kind of depends on your use case. So through MLJ, you may have less power about the sort of model that you could, the sort of deep learning model that you could do, but by the same token, the sort of meta stuff that you might want to do may be far easier to do if you just work from MLJ. Someone's asking, where can I access the notebook? I'm assuming that's someone that's come late. So that's a fair question. So to access the notebook, you go to maybe I'll just look at we go to this repository. So if you go to this repository, you'll find instructions on how to run the tutorials that we're looking at here to get these notebooks. So I've answered that one. There's a question here which is asking, is it possible to get the exact within my first n most high probability estimations? I'm not sure I understand the question. Maybe if you could give a little bit more context, I'll have a go at it. So initial compilation of all packages takes a good amount of time. Is there a good way to speed up this task? Use multiple threads, cores on a CPU. So that's kind of two questions. So in terms of compilation, when this notebook is, so there's a lot of different models that I'm decided to try and integrate into the notebook for the sake of variety. So that means we're actually loading in quite a few different packages. MLJ does, you know, it is a bigger package, so you're never going to have like something that loads in, you know, 1 second. there's no really real way around that, except you will save time if you just so in the notebook and the environment, depending on how you ran the notebook, you may have already preloaded more packages than you needed. That's what I'm trying to say with the setup. So it's possible that the time could be less if you're not using all the models, but there will be some compilation time the first time you use MLJ. The easiest way to test that is just to put MLJ by itself in a new environment and just load it, or actually, yeah, just install MLJ and run it and see how long that one takes. Do we have support for multiple threading and multiple cores? And the answer is yes. Most of the meta algorithms can be parallelized. Let's see, the resampling can be parallelized either with multi-threading or distributed, and the same goes for the tuning. And you can nest those things, so you can have parallelized tuning, and within that, when you're resampling to get each tuning, each model estimate, you can also accelerate that as well. Although there's limits on what a combination of those you can do. So I'm still not quite sure I understand the question exactly from about the first or second best predictions, but the point is that I can say this: what is returned is a probability distribution. So whatever information you can extract from a probability distribution, you can do so. So I mean, there's no information missing, unless your question is asking about a different kind of prediction altogether. I mean, some models predict intervals or something, for example. Not currently any models in MLJ, but that's another kind of prediction. But if you're talking specifically about predictions, I guess that's the best I can do to answer that particular case. There is an exercise in the tutorials where the question asks you to say, for a probabilistic predictor, so I want to know for each observation, what is the predicted probability of the observation that I actually saw, right? So that's something, there's an example that shows you how to do that as an instance, but I'm not sure that it addresses your specific question. I think that's the best I can do at the moment. So if you have a question that you feel wasn't answered adequately during the workshop, do have another go by posting an issue, because then we can take a more measured response to what you have to say and get extra context and so on. I think I want to block that one. So I'll let you guys play around for another 5 minutes. I'm not getting any questions specific to the exercises, which has me wondering how many of you are actually managing or finding that useful. Here's the chat. Do I understand correctly that MLJ is a sort of umbrella? This thing keeps this umbrella for lots of different existing machine learning packages. That's exactly what it is. It's a uniform interface for interacting with machine learning models in different packages. But on top of that, there's these meta algorithms for evaluating their performance, and for optimizing their parameters and so on. So someone asked, what does the name refer to in the unpack function? That's just a dummy variable. So so I could put anything there. It's just that the trick is to put a function there that always returns true. So that function is it's a lambda function. So that's just a trick to say, well, I want all the rest of the variables. So I could have gone X maps to true, for example, and it'll have the same result. Okay, here's a good question. Surprised that I got 0 results when I did a search for models matching some data when one of the data was an ordered factor. So there's actually very few models that will, at the moment, that will handle categorical data. So, I mean, that's the same as true if you look at scikit-learn models. Now, I should like to think there was at least a decision tree that would handle categorical data, but so we haven't one of those so far. You can give a decision tree ordered factor data, I think. I'm not sure why, what the complete story is with your data. So there may be some models that can handle ordered factors, but a lot of models want things continuous. And of course, in that case, what you then need to do is to convert your, the common strategy is to convert your data into continuous data. And we're going to talk about that in the next section. So we'll talk about one-hot encoding or continuous encoding. So you'll have an extra pre-processing step that you need. And so the model's matching thing isn't going to help you there. You would want to apply that model's matching method to the transform data to then get a better sense of that. Later, we're hoping to kind of improve that functionality in various ways, but I'm probably not going to get into that here, so that the searching would kind of account for that kind of common pre-processing steps that you could imagine taking. Someone's having trouble pre-compiling CSV again, and I'm not sure. It seems that that's not happening for everyone. I understand one suggestion is to try using, see if you have the same problem when you just run from the Julia REPL or from Juno. I'm not sure how to answer that specific thing. I'll leave the question open in case someone else wants to pitch in. Load error, too many parameters for type.
Anthony, I've answered that before. It's I think it's an issue with Julia Pro package. It works with
Okay.
when you download Julia from the website julialang.org.
Okay, so in answer to you, Vincent, with your pre-compilation problem, it seems to be an issue with using Juno. So if you download Julia itself, not bundled in Julia Pro. Is the issue with Julia Pro? Did you say, Samuel?
Julia Pro.
Yeah. Okay. So instead of using Julia Pro, just download Julia itself, and that should resolve the issue. I'm not. I think you'll still be able to use Jupyter. You'll be able to use a notebook but then you will have to use iJulia so that's a longer story, and I probably don't have time to try and attempt an explanation of installation. You're probably on your own for that. But Julia, the issue, as I understand, is with Julia Pro, not with using just ordinary Julia. Okay, now I'm going to return to the notebook. To presentation and move on to the next part of our presentation, which is here. And we're going to look at, so if you've come late and you're wondering where the solutions to the exercises are, they're at the end. And now we're going to talk about transformers and pipelines. We have about an hour left. So this discussion takes about 20 minutes and another 11 minutes for the final part. So we have about half an hour more of me talking and half an hour of you to work on your own. So I think that's fine. I think that we're going to be okay. So let me have a go. Let's move to transformers and pipelines. So transformers, more or less, then there's not a big difference between transformers and training transformers or unsupervised models compared with supervised models. It's actually just simpler. You don't have a target to worry about. The other difference is that every unsupervised model will have a transform method. It may not have a predict method, although some models, say for example, clustering models will often have both. But there will always be a transform method. So let's have a look at an example of a transform. And this example is simply a transform that takes a vector and normalizes that vector. So that is, arranges it to have zero mean and unit standard deviation. So we'll take a vector of numbers between 0 and 1, chosen uniformly at random. And we see that this vector has non-zero mean and some non-unit standard deviation. So now what we do, we're going to instantiate the standardizing model. And this one is actually built in. So a number of the common transformers are built in, so you don't have to use that at load syntax. You can, it won't make any difference, but you don't have to. You can just instantiate the model by calling it with a name. We'll see how you get a list of these later, with brackets, and that will use the default hyperparameters for the standardizer. I think, in fact, standardizer doesn't have any parameters. Oh, it does for tabular. In the tabular case, it does. Okay, so you instantiate the model, step 1. Step 2 is you bind that model to the data, which is just a single vector in this case, and then you fit it. And in this case, we'll fit to all the data by just omitting the specification of rows. Once the model is fit, we can apply the transform method using that machine we've trained to our data X, or we could transform some different vector, but according to the scale that we learned from the vector X, okay? So that's what we're going to do here. And then at the end, we'll show what the mean and standard deviation is of the result. And when we do that, we see that we get what we want, zero mean and unit standard deviation. So this method has another operation. In addition to transform, we can do inverse transform. That's not true for all the transformers, but it's true in this case. And when we do that, we get back to where we started if we apply the inverse transform to the transform of X. So This is approximately true. Now, for further illustrations of common transformations, we're going to have a look at this King County house data, which I think is part of one of the exercises you had a look at. And now we're going to address that question that was raised earlier about data that has categorical features, and hey, help, there are no models that, well, not many models that deal with non-continuous features. So we're going to make the features continuous with a transform. And what we want to do is, we could use one-hot encoding, but then that would only deal with the multi-class variables, and it wouldn't handle, say, for example, count data. I mean, it would be fine to use the one-hot encoding, but if you want to be sure that everything gets transformed into a continuous variable, we use this continuous encoder. And what it does by default is it will one-hot encode all the multi-class features. It will take the ordered factors and it'll just convert them to continuous features, but without spawning, without one-hot encoding. So just one feature will become one continuous feature. It won't get spawned into a number of features. And then it'll also coerce the count features to continuous, sort of in the obvious way, because a count is already just an integer. So now it becomes a float integer. In this case, there aren't any. And then it also drops any remaining non-continuous features, which what the one-hot encoder doesn't do. So this is to force the fact that we want only continuous features. And in this case, there are no features that will be remaining. Everything will be taken care of. So let's do that with the house data set. I'm going to reload it and apply the type coercions, which ensure that our data is going to be interpreted correctly by all MLJ models. That was an exercise which I'm not repeating here. I am repeating it here, but I'm not explaining it again. So that's just loading the data and having a look at the schema. So these are all good. And we see a mixture of multi-class, ordered factor, and continuous data. So now we're going to unpack the data. And since we're interested in predicting the price, that's our target. And then everything else is going to go into this X. So that this name maps to true is just a function that for any input called name always returns true. So this means, everything that's left over after I pick off the price is going to be unpacked into X. So let's unpack that. Let's instantiate this new transformer, which is called continuous encoder. It has some options, but we're just using the default values. I'm not going to talk about too much the options for now. Then it's going to behave as I've just described with the default hyperparameters. Let's now bind that to that model to the data, which now is a table. Before it was just a vector, but now it's a table. And that gives us a machine that we can fit. Here's a little bit of Julia syntax that beginners may not have seen before. It's a pipe syntax, which just says that I'm going to apply the fit method to everything that came before. So if you just have a single argument that you want to give a function, this is sometimes convenient. So now we're fitting our encoder onto our data, which has some multi-class and ordered factor variables. That's done, and now I transform. So I'm going to transform using the machine I've just trained on the actual data. I'm using all available data. I'm not subsampling here. And call the result xcont for xcontinuous. And let's have a look at the schema for that. And now we see a lot more features because we've one-hot encoded. So I think there was just one multi-class feature actually in the end. All the others were ordered factor. So that's zip code got spawned into a bunch of features. So that's how transformers work. If you want to see what all the transformers available are, all the unsupervised models, you can use this models function as we talked about before and give it this particular filter. I'll do that. And there's 28 different transformers. That includes the built-in ones. Here is a list of some of the commonly used ones that are built in. So we have continuous encoder, we have a feature selector, which just basically picks off certain features. You can do impute missing values. You can do one-hot encoding. You can normalize your data, whiten it, however you want to call that. And there's a box-Cox transformer for vectors and a discretizer for vectors. In addition, often you want to just transform your data using some function. So there may not be something that you're really learning per se, but nevertheless, you may want to wrap that function as if it was a model, because you want to stick it in the pipeline, as we've discussed later, and so on. And you can do that. So there's ways to construct your own static transformers, if you like, and they can have parameters, so that become the hyperparameters or fields of your struct. And there's simple ways to do that, but I'll refer you to documentation to learn how you do that. For now, I'm going to talk about pipelines, which is the simplest way of composing things, composing models, where you just stick a number of models in sequence, in a non-branching sequence. So let's have a look at this continuous vector that we just constructed. I'm going to compute the number of columns it now has. So it has a lot of columns, 87 columns now, because we did this one-off encoding. Now, and I probably might decide that that's too many features for your supervised learner to handle. So we've got our data now, we want to do supervised learning on it. So we may want to reduce the dimension. So let's look at an example of that. Now, there's a model for reducing the dimension. There's different models, but let's pick one approach, which is this PCA model, Principal Component Analysis. We'll load the code for that defines that model and instantiate it with this line here. So now we have our model in scope and an instance of it. Now, what we could do is now just repeat the same workflow we just did. That is, we bind the model to a machine. We bind the model to data in a machine, and then what data would we use? Well, we'd use the continuous features that we've already got, and then we would fit that and transform it and so on. But that seems like not a very efficient thing to do, since after all, we might want to do this over and over again when we get more data, or maybe for a different model and so on, a different data. So what we want to do is combine these two models, the one that encodes things as continuous and the one that reduces the dimension, into one combined supermodel or composite model. So the way you do that is with the pipeline syntax. So we'll be learning, well, we won't be learning probably today, but late in the final bonus section of this workshop, you can learn about a more flexible way of composing models. But this is a canned version that is the most common use case, which is pipelines. And this is how it works. You simply list the models in the order you want them to be composed. So we want to first apply the continuous encoder that we defined already, and then the reducer that we just defined. Incidentally, if you like, you can just put model types here. You don't have to put instances. So I'll run that code, and that will construct, it will actually define a new type, a new model type, which is called pipeline 374. And it'll instantiate that type using the as default hyperparameters, the one that come from the components, and call that pipe. So now this model, this composite model, just behaves like any other transformer. It's a composition of transformers. And so you can bind it to the original data, not the continuous data that we already transformed earlier, but the original data into a machine. You fit the machine, and then you transform your data using that machine. So, and then we'll call the answer X small because it's now going to be reduced. And so that all works. So we now have this reusable composite model, which is a combination of encoding and reducing. And we see this model actually decided, because the PCA, by default, it'll just throw away kind of everything but 1% of the variance. That's something you can adjust, but we didn't. And in this case, it turns out that leaves just two variables after we reduce. Now, it's a linear model, and we are probably throwing away a lot of information, but that's what PCA does. And so that's a simple pipeline. Now, suppose we want to add to this pipeline a supervised learning exercise. Suppose we want to take this data that now has the right form, namely the features are continuous and there's not too many of them, and we want to apply, say, ridge regression to that model. So this code here first loads the model code, instantiates it, this regressor, calls it RGS, and then it puts it at the end of a pipeline. So it's the same code we had before, except at the very end we've put regressor. And we'll call that new model pipe 2. And now this model is a supervised model. So it's a composite model, but it's supervised because we put a supervised model at the end. Now you don't have to put your supervised model at the end. Maybe you want to perform some transformations to the output of the supervised model, the prediction output. So you can put them later, but the more common case is to do a combination of transformation and inverse transformation in your target, but I'll talk about that in a sec. At the moment, we're just encoding, reducing, and then applying ridge regression. And that model now is just like any other supervised model. We can bind it to the data, the original data we started with, and in a machine and evaluate that machine, say. So instead of doing fit and predict, I'm just going to evaluate its performance on all of the data using a holdout set. So there's a question here, which is I just see, what is the difference between transform and predict in the pipeline context? So in the pipeline context, the pipeline macro will do its best to infer, well, I mean, it will be able to infer whether the model should be regarded as supervised or unsupervised. If it's an unsupervised model, it'll have a transform method. If it's supervised, it'll have a predict method. Now, if you want to do something fancier and you want a composite model which implements multiple methods, say for some kind of composite clustering model, where you have both a transform and a predict method, then you can do that, but you can't do that with the canned at pipeline syntax. So you would need to use the generic model composition syntax, which won't get described today, but it's possible to do that. Now I want to explain the sense in which training of composite models is smart. So I'm going to fit that machine, and we see that it's fitting along the way to a continuous encoder, and then the PCA, and then the ridge regressor. Now what happens if I change one of the hyperparameters of the very end of the pipeline, which is the ridge regressor? And notice here we've got a nested hyperparameter here because the pipe is a model which has as a field another model, the ridge regressor. And then that has its own hyperparameters. So let's change that lambda, that regularization parameter, to 0.1 and refit. And you'll notice something interesting happens here. Now it says not training continuous encoder, not retraining the PCA, updating the ridge regressor. So because this model becomes later in the pipeline, MLJ automatically realizes that it's not necessary to retrain those earlier components of the pipeline, because only a parameter for the final component was altered. So it's clever that way. I mean, if I change a different parameter, then some different things will get trained depending on where in the pipeline I make the change. So there's another demonstration of that. Okay, so next, I'm going to talk about inspecting composite models. So suppose that I want to look inside my composite model that I've just trained at one particular component and see what the fitted parameters were. So you use the same function that we talked about earlier, the fitted params function. You apply that to your machine. That was the machine corresponding to your composite model. And then you just pick off you use the dot syntax. You pick off the component that you're interested in. So for example, the ridge regressor, you just add using dot syntax, you tell us which bit you want to look, and then you get the coefficients. And the same goes for the report. So if I want the report for the PCA, I add dot PCA to my report, because now my report is sort of a name tuple with lots of keys, one for each model. and I can see various output associated with the training of the PCA. Now, the next thing to talk about with pipelines, which is sometimes the source of confusion to beginners, but I don't think it's the place here to explain target transformations. I'm assuming that you know what I mean when I talk about target transformations in the pipeline context. In a nutshell, what the idea is that when you have a target variable that you want to transform, you apply some transform to it, and then you goes through the rest of the pipeline. And then at the end, once you get your predictions, you want to apply an inverse transform that you learnt previously, so that the target has the representation you started with. So to take an example, if we look at the housing data, you may not want to apply your regression to the price. It may make more sense, depending on the model, to use the log price. And that's a common practice when doing in the housing market, is to build models using the log price and not the price, because it makes a difference. The models will train differently. Yet at the very end of the day, you want to look at the price and your metrics, how you evaluate performance. You may want to phrase those in terms of the price, not the log price. So that's why we want to transform data, but then the target, but then also inverse it at the end. So here's how that works. Suppose we want to take the log price, then you can take these functions. Here I'm just overloading log and exponential to work on vectors, because they don't by default in Julia anymore. So these functions that I put here have to be functions that act on the data as a whole, not just one observation. And I give keyword arguments. So I have my pipeline, it encodes and it reduces and then it applies a regressor, but I want to combine that with the target transformation. I want to take the log of the target, and at the end I want to invert that using the inverse of the log, which is the exponential. So that's the syntax for introducing target transformations. Now, what you can also do in MLJ, which you cannot do in some other frameworks, is these don't have to be static target transformations. They can be learned target transformations. So the inverse that you apply at the end will use the learned transformation that you used at the beginning. So instead of specifying here a function, the only difference in this case is that you specify a transformer now. So let's suppose we want to compare two different kinds of target transformation, a univariate box-Cox transformation and the standardizer. So the standardizer can be univariate or tabular. It works for both. So then what we do here is we just specify that transformer instead of a function. And we don't need to specify an inverse transform, because this is only going to work if those models support the inverse transform operation anyway. Right. So that's how that works. So now first of all, what I've done here is I've taken the box-Cox transformation, applied that to the target, and I'm doing an evaluation, which by default, by the way, is cross-validation. So there's a cross-validation estimate of the mean absolute error. And now I'll mutate one of my models in my pipeline. I'll change the target transformation from the box-Cox one to the standardization one, ordinary whitening of the data, and reevaluate, and then I get a much better estimate in that case. I get a lower estimate in that case. So that's the end of transformers and pipelines. And I'll stop talking now, and I think we'll give you another 15 minutes to play around yourself and maybe have a go at the exercises, and I'll look at some of the questions. Okay, here's a good question. Do composite models store all the intermediary data between steps? No, they don't. They do not cache, but they do not cache the data. So everything everything is done in a sort of lazy way. So and you're saying here that I'm assuming so, since it's able only update the last step, for example, in the last example. Well, the training is intelligent in the sense that it will know whether the data that so when you call a composite model and you retrain it, it's sorting all that out. So it will figure out whether, due to the model changes that have happened, the hyperparameter changes that have happened, whether the data that it will receive will be in a different form or not. So it will have to recompute. If something happens earlier in the model, then because nothing is saved, it will, well, what am I saying? Now I'm tying myself into knots. But the basic answer is no, we don't cache data. But yes, the model will only, update if it's something that it can do without mucking things up. So the thing is that what's happening, there's two different phases, right, in your model. There's training the model, and then it's just applying predict or transform to the model. So if the model learned parameters haven't changed, you just recall predict. And often, the predicting part of predicting is usually much quicker than retraining. So, but when you're asking about whether the so there's no real need to cache the data, because to get the data, you just recall predict. But if you know that predict is going to give you something different, then you know that you're going to have to retrain before you pass on the prediction or transformation of that next phase, if that makes sense. Okay, so here's another question. Is it possible to specify the data subset used for composite models in the pipelines? For instance, use the pipeline macro to apply one hot encoder for the subset of features and apply PCA for a bigger subset of the features. So it is certainly possible. There are different ways that you might go about it. Now, you can do anything by just using the generic composition model syntax, which I'm not going to have time to talk about today. But within the pipeline, so I mean, you have transformers that will select features, but here you want to do something in parallel, right? Because you want to split off some of the features and do one kind of transformation, and split off some different features and do another kind of transformation. So to do that, it's probably beyond the basic capability of the pipeline syntax, but you can easily do it using the more general learning network syntax that we won't have time to discuss in this workshop. But there is a section on that, I mean, in the workshop. So if you look at part 5 and you work through that section, you may get the gist of how that might work in your particular use case. So I'm not quite sure how to answer this question. It says, if you use RNN, so recursive neural network, or an LSTM on this iris example, how will it work with the prediction? Well, recurrent neural networks are not something that are currently, we don't have an interface for working with those kinds of networks. So we have there's a package called MLJ Flux, which provides the interface for some neural network kinds of neural networks to MLJ. this includes, if you go visit the site, you can get some more details, 4 different models. So one of them is just an ordinary regression model, and you have control over, so maybe I'll say a little bit of, well, let me just give you the big picture first. So there's a regression model, there's a classifying model, there is an image classifying model, and there is a model for multi-targets. So when your target is more than one column, if you like. And so the recursive neural networks don't exactly fit into the framework of those basic model types. Now, the basic idea of the MLJ models and interacting with Flux is that the detailed architecture of your neural network, it's going to depend on the actual data that you give the model. So when you have a parameter there, a hyperparameter in your Flux models. Maybe this was somewhere earlier in here. I'll see if I can find it. Probably the first time we did Flux. Oops. Right, so here's an instance of a neural network classifier, which is a model that interfaces with Flux. So there's this thing called a builder, and all that is it's a neural network. It's with just a single, I think it has a single hidden layer and a dropout. And but the number of input, because it's a classifier, the number of output features, the final layer of your neural network, the size of that is going to, of course, depend on the number of classes you have. So in this situation, you're not actually specifying the neural network architecture. You're specifying a kind of recipe for how to build that, so that once the model sees the data, it can finish building the network, if you like. So the beginning, sometimes the beginning, and sometimes the end of the model of your neural network will have to be modified according to the data, or even internals of the model. You might want to change those depending on the data. So you have to kind of to write some kind of recipe for how you go from actual data to a neural network architecture, and that's all specified through this thing called a builder. And if you want to learn more about it, you can go to the documentation for MLJ Flux. I think that probably answers this question. If it doesn't, then Binto. So if it's not, then re-ask your question, or you can always just open an issue on that website. Oh, okay. So coming back to Ben Tang's question, yes. So yes, of course. I think I miss. Now I understand your question. So yes, of course, the pipelines do cache the learned parameters of the models. They just don't cache data. So if you have a pipeline, then of course each component of the model is going. There's a machine, in fact, within the model which is storing the learned parameters for that model. But the data itself at each point in your pipeline is not cached. Okay, great. Sorry for the confusion. So we have another about 5 more minutes of playing around. So Jose has an outstanding question here about context variables. I'm going to suggest that it sounds like it may be a kind of a feature request. If you could raise that as an issue either on MLJ, or if you think it's maybe specific to scientific types, you could raise it at the MLJ scientific types website, but it doesn't really matter. MLJ would be fine. And then we'll try and address that a little better there. So another minute or so, and we'll turn to the home stretch. Oops, I don't know why that didn't. So yes, we've had a question about, or perhaps I'll just answer that. So if all encoders had arguments to leave some collars untouched, then we could easily apply encoders in parallel. Yes, that's actually true. And you can specify, so for example, so not all transformers would leave you the option to leave some columns untouched. Some transformers do. And I think there's an issue that's been raised to create a kind of generic transformer that might solve this problem in some cases, where you specify a univariate transformer and you just apply that to all columns matching some criterion. So I guess the answer is you've answered your own question. That in principle, you could still use the pipeline to do some transformations in parallel, as it were. So takes, applying reduction to some subset of the features, and then maybe applying one-hot encoding to some other subset of the features. I'd have to let's see, the one-hot encoding. I think you can specify the features, but the dimension reduction would be the problem. But then what you could make you could have a pipeline within a pipeline. So you could have a pipeline that combines feature selection with dimension reduction, and then I suppose then you have to splice in the two. I'm not sure if that works. I have to think about it a little bit more. Great. Okay, so now I'm going to turn to the final stretch of tuning hyperparameters. How do we do tuning, which is like most important part, really. Okay, so already you can sort of proceed in a naive way if all you want to do is tune a single parameter. So if you want to tune a single parameter, you can use that learning curve method that we already talked about. And let's just see that in practice real quickly. If we look at the horse data that we've talked about, and we put a logistic classifier in a pipeline with transformers that standardize the input and the target, then we get a machine, and then we put that in a machine. Now we specify a range to use in our learning curve. And this case, remember in our other example, it was a neural network, and we used the epochs. But now we have a composite model, and we want to specify a range of, say, the regularization parameter for the logistic classifier. So that's one of the components of the model. So then you now have in this range syntax, you have this extra dot, right? Because you have a nested hyperparameter. You still need the colon at the beginning, but everything goes in brackets. And so that's the kind of new thing when you're dealing with a nested parameter. And the rest is sort of as normal. You have a lower and upper bound and a scale. So let's define that range. If you're curious and you want to kind of see what sort of values that range is going to give you once you specify a resolution, which is going to come up, which would come up if you were doing grid search in the more general situation, then you can look at this thing called iterator. So if you have a range and you apply this method called iterator to it and specify a resolution, then it'll tell you what numbers will get generated. So you can see this is 5 numbers on a log scale. And resolution is something that you can specify when you call the learning curve. And so that if I put resolution equal to 5 here, then these are exactly the lambda values that are going to get used to generate the learning curve. But here I'm using 30, which happens to be the default. And this time, instead of using a holdout, I'm going to do a cross-validation resampling strategy to get my estimates. And everything else is as we've seen before. Now, to pick off the bits that I want to plot, I'm using a shortcut here, which is to ignore the first bits that I don't want to worry about, and just pick off the lambda values and then the losses, which are the last 2 bits. So you may remember that this learning curve is some kind of named tuple with a bunch of stuff, but you can actually peel off things from a named tuple this way as well. And then I'll plot the results of that learning curve. See, what model are we using? A logistic classifier, logistic regression, which is really classification. Right, so now there we go. You get a plot. So that's one way to proceed. And then if you wanted to get the optimal parameter, then you could just use your argmin function to figure out that best value. But we want to be a little bit more sophisticated than that, and we may have multiple models that we want to tune, for example, at the same time. So the first thing to understand about MLJ's approach to model tuning is like, and we get this inspiration from MLR. I suppose it's done elsewhere as well, I'm not sure, which is that tuning is implemented as a wrapper, a model wrapper. So what that means is that you take a model that you want to tune, and then you create a new model, which is sort of like that model wrapped in the kind of tuning you want to do, as we'll describe in a minute. And then you can think of that new model as a kind of self-tuning model. So what that means is that when you take the wrapped model and you fit it, then that fit takes the atomic model, the inside model, optimizes it according to the strategy that you've outlined and the parameters you've picked out. And then once it's found the best model, it will retrain on all available data, and then it'll cache that, it'll store that result. Then when you go to predict on the wrapped model, the self-tuning model, that will give you a prediction as if you were predicting on a model trained on with the original model on optimized hyperparameters. So now I've said all that, it's sometimes a bit hard to get your head around that, maybe it'll become clearer if we look at an example. So there's stacks of tutorials on MLJ that do grid search. So I thought for variety I should do a different modeling tuning strategy. So we're going to use a random search instead. There's another option which you can use, which is tree parts, and I'm not going to look at that here, which is actually a third-party package that was provided to us by the Equivia people. So let's have a look at random search. Random search has a bunch of parameters, and these parameters control the default prior distributions that are going to get used for your sampling. So random search is sampling the different hyperparameters according to some distribution that you can specify, but by default, MLJ will fit a uniform distribution to bounded ranges, a gamma distribution to positively unbounded ranges, and a normal distribution to anything else. And we'll only use that default behavior. But you can essentially specify any distribution as a prior that you want. So in MLJ, a range doesn't have to be bounded. So in this example here, I'm looking at the logistic classifier component of that pipeline, and I'm looking at its regularization parameter lambda. I want to start at 0 and go off to infinity, if you like. So I just don't specify an upper bound. But if I don't specify an upper bound, I will be required, and the constructor will remind me if I forget, that I need to specify basically a center and a scale, or what we call here origin and a unit. And we saw earlier in the learning curve that this parameter optimized at around 5.5 or something. So I'm going to pick as my center, as my unit of scale 5, and my center, my origin is 6. So what that will mean in the case of this gamma distribution that's going to get fit is that the gamma distribution will have a mean of 5 and it will have a mean of 6 and a standard deviation of 5. So this is kind of specifying parameters for the distribution will need to fit to that. So let's define that unbounded range now. And to give you a little, and this is kind of going into some details you don't need to worry about if it's not so familiar, but I want to just go through it quickly. If you are curious about what the sampling will actually look like, you can construct a sampler object with your range and the given distribution you want to fit to it. In this case, we're going to use the gamma because that's what the random search uses by default to give us an idea of what sort of samples we'll get. So I'll construct this sampler object by just going sampler, my range, and the distribution, and then I'll plot a histogram of 10,000 samples. Oh, why didn't that happen? Somehow distributions is not in scope. Not sure why that is. Maybe I missed it. And you probably, oh, I know, I made a last minute edit to this file. That's probably the reason. So I'll fix that by going import distributions. Hopefully that will fix it. Right, so now we see here's a gamma distribution that got fit. I mean, this resembles the gamma distribution. So we'll have lots of values around the 5 and 6 area, but not so many once we get out to say 30, a value of 30. Okay, so now that's one parameter taken care of. Now let's specify a range for a different parameter, and we're going to go to a different part of the pipeline. We're going to look at the one-hot encoder, the continuous encoder. And this is a parameter which says whether or not we should one-hot encode the ordered factors or just go straight to one single continuous feature. And that only has two possible values, true and false. So rather than specifying, upper and lower bounds, we just specify the values. So that's true for any nominal kind of hyperparameter. So now that's defined. We've got our two hyperparameters defined, and we won't do any more in this illustration. So here is we'll interrupt the flow I'll take that question at the end. Okay. So now to the tuning wrapper. So we've got our model, which happens to be a composite model, a pipeline, which we called model. Remember that was, I think it was a logistic classifier with some encoding. So some normalization or making things continuous or something. So this is what we do. We now defined a new model, which is a wrap of the original one. So to wrap, that means you specify as one of the hyperparameters a model, the thing that we want to wrap, and then how is it that you want this tuning to be carried out? So specify some ranges, the R and S that we just defined, a resampling strategy, the measure that you want to use to construct your objective that you're minimizing or maximizing. That will be incidentally automatically determined depending on the specific metric that you put here. So some could be a loss or a score, it doesn't matter. And then the tuning strategy you want to use. So you've probably forgotten what tuning was. Tuning was this random search. So back up, gone past it. I've lost it. It's even earlier, isn't it? Here it is. Tuning is random search. So that's the tuning strategy we want to use. Could be a grid, but I'm going to do random search here. So then, and then finally, the number of iterations. So all tuning is implemented in MLJ as an iterative procedure, even grid search. And we're going to, so in this case, we'll do 15. We'll try 15 different combinations of parameters by sampling 15 times. Each time once from R and once from S, those two ranges. So that's what that thing looks like. And now this is just a model like any other. It's a container with a bunch of hyperparameters specified. We can bind that model to data. So now I think this is the horse colic data, or is it the price data? I've forgotten now. What are we doing in this demonstration here? The horse data. So we've got the horse data. We bind it to our wrapped model and we fit it. And that, as I explained earlier, this fitting will mean that under the hood, the optimization happens. And then when we predict, prediction will be like predicting on the model as if we already magically knew what the optimal hyperparameters were. And it set them to those optimal values. And so there's 3 predictions for you. Now you can inspect the outcomes of your tuning strategy. So you might want to see how the tuning goes. It's all very well to wrap it in a, to do this wrapping, but you need to go under inside to see what happened, because you want to get those details. And you can look at the fitted params and the report for that. We'll have a look at the report. And in the report, you'll find something called best model. And there it is. There is the best pipeline model that it came up with this lambda of about 5.1. And it turns out that it was a bad idea to one hot encode the, no, that's not right. It was a good idea to one hot encode the ordered factors. Interesting. Right. So then we can also, and there's not a lot of this functionality yet in MLJ. So if you're interested in graphic visualization, there's an opportunity for you. But if there's just 2 parameters, we can get a plot. And what we do is we call plot, and there's a plots recipe for machines. We're tuned to model machines, and we can get a plot. And we've just done 15 things here. We have it looks a bit funny because we've got an ordered factor. We've got a nominal with just 2 values, true and false. And the small circles mean low score and low loss, and the big circles mean high loss. So this is where we want to be over here. And so now we have this machine, this self-tuning machine, we can evaluate its performance just like we would any other machine. And what I'm going to do first, no, I'm sorry, this is the original machine that was not self-tuning. And then for comparison, we're going to evaluate the performance of the tuned version of that thing. And in the second case, we get an example of what's known as nested resampling. Because here we're resampling because we're doing cross-validation. But each model itself is doing resampling to optimize the internal hyperparameters. And if you're interested in this nested resampling business, you can check out a link here. And that is the end of me sitting here and talking to you. I'm going to now let you play for the remainder of the time, which isn't very long, another 8 minutes. Sorry, I ran a little longer than I thought, and have it try to answer any questions that are left. So the question here is, how do I know that the max depth in EvoTree classifier is called EvoTree classifier.maxDepth? That's a good question. So let's have I'm going to step back and look at that. Well, that was exercise 7, wasn't it? So I'll just look at I'll look at this thing. I'll look at an earlier example. Let's go to the top. So when you construct a pipeline, then that does two things. So here's this example that we looked at earlier. It constructs a new model type, and the new model type is automatically generated as pipeline 374. Now, whenever you have a model and you want to know what the features are called, you just put the model at the REPL. So let's just escape that. I'm sorry, let's go down. Let's evaluate this again. Hopefully these things still make sense. So if I have a look at, if I just type pipe, and I have a look at that, I get a representation of this model, and I can see what the features are called. They appear on the left. Now the question may be, how did it come up with these particular names? Because this is a struct with field names now. How are the field names decided? I think that's the question. And the answer is that it gets the names from the type names. And if you have more than one, for some reason you have 2 continuous encoders in your pipeline, it'll generate, it'll put a 2 on the end or something like that. So these names, in the canned version of model composition that we're using here, this pipeline, these field names get automatically generated. And you can see what they are just by just having a look at how that thing gets displayed. In the case of more general model composition syntax we don't have time to talk about today, you can specify the names, whatever names for the fields you like. And in the case of a pipeline, you can specify the name of the pipeline type itself. So if I wanted, I could change this to my pipe, say. You didn't like that name, or you wanted some reproducibility for various reasons. You always wanted the name to be the same because for some reason you're going to have multiple pipes. Then you can overload them. You can say exactly how you want your pipe to be called. But you don't have a choice about what the field names are called. They get automatically chosen based on the types of the models. And if you don't like that, then you have to use the more general syntax for building composite models, which I'm not getting a chance to talk about. So I'm going to hang out till the very end, which is 4 more minutes, but I'm going to take this opportunity now to thank my helpers, my collaborators, Joffrey Dolphin, Sebastian Vollmer, Thibaut Lienhardt, who had to leave earlier, Samuel Ocon, and I've probably forgot at least one person. Where's my list? You have to all remember that this is 5:30 in the morning for me. So I've been up since 2 in the morning and feel like I'm jet lagged. it's been quite hard getting used to getting up at this time. So yes, I thank my helpers, Thibault, Joffrey, Ocon, and Sebastian. Yes, I remembered them all. And thanks for coming and participating, and thanks for your questions, and for feel free to post issues and so on. Blah blah blah. Now I'm looking at another question. So, so we come to the end of the workshop for those that are still here. I can see an amazing 71 people. We started with a little over 200, I think. So I don't think that's too bad. And most people have sort of left in the last hour, I think. So that's great. Thanks for coming, and appreciate all the feedback. I'm now closing the meeting. We'll see you around the virtually around the conference. Thank you.